Hey, welcome back. Okay, so we left off rather abruptly on the idea of the inverse square law. So this is called the inverse square law. And it's what you get when you try to measure intensity of something that moves in all three dimensions when you measure it over a single dimension. Okay, so imagine when I'm talking, my voice is going out in three dimensions. And if we were to measure the intensity at one dimension, that leaves two dimensions that we're not including.
Yeah.
Does that make sense?
Okay.
So because we're looking at two dimensions that are not included, we have to square how the intensity falls off with distance.
Wouldn't that, I thought it would be used for this.
One would think, yeah, but it's square. So this works with light as well, and basically because waves move in all these dimensions. If you say, all right, if I'm 1 meter away, my sound intensity is X. If I go to 2 meters away, I double my distance, my sound intensity is going to be 1/4 X.
Your brain sounds bigger.
Make sense? Okay, so when you double your distance away from a source, the intensity falls off with the square of distance. If you double the intensity, you double square the denominator.
Wouldn't you say that assignment would be like
This?
almost figure 8?
That's varies with.
Very
Yeah, so varies with. It means there's a bunch of other terms that we're not including.
okay.
So we're saying I varies with 1 over r squared. So there's a bunch of terms, like early on I said force of friction varies with the square, it equals, varies with the square of velocity. So there's a bunch of other terms that we're not going to include. So similarly, volume or sound intensity varies with the square, the inverse square distance. In other words, if you have, back again, my analogy, let's say something has X loudness at 2 meters. If you double that to 4 meters, there's going to be 1/4, not 1/2 the loudness. If you double it again, it's going to be 1/8 because that's 1/2 cubed. Okay, does that make sense?
Yep.
So light intensity and sound intensity and a lot of other things fall off with the square of distance. This is called the inverse square law, and it pops up a lot in physics. So things fall off with the square of distance. If you double the distance, you quarter the intensity. If you triple the distance, you 1/9 the intensity. Make sense? Because 1 over 3 squared. All right, cool. So again, inverse square law. And again, we also talked briefly about the decibel scale. And for reasons that no one knows, the decibel scale, they put a 0 after it. It's a logarithmic scale, just like the Richter scale. And for some reason, they're like, let's put a 0 after it. I don't know, maybe Alexander Graham Bell loves zeros. But yeah, so when you go from 1 to 2, it's 10 times more powerful. An earthquake of 6 is 10 times more powerful than an earthquake of 5. And an earthquake of 7 is 100 times more powerful than an earthquake of 5. Well, works the same thing for decibel scale, only now we have a 0 to it. So a sound intensity of 40 is 10 times more than a 30. And a 60 is 100 times more than a 40. And a 90 is 10, 100, 1,000, 10,000 more powerful than a 50. That make sense? Okay, so that's how the decibel scale works. If you're curious about how sound energy is measured, it is measured in watt per square meter. Watt per square meter. Watt is a joule per second. It's power. So it's power over area, watt per square meter. That's how we measure sound intensity. It's how much wave energy is traveling through a box. How much wave energy in watts is traveling through a 1 meter square box. Okay. So, how are we doing? Good?
Quite dang.
Okay, I want to show you something. Again, old toy, really old toy. So hopefully the string won't break off. But I got this buzzer at Radio Shack. It's just a standard 3 kilohertz or 3 hertz, 3 kilohertz, 3,000 hertz buzzer connected to a 9-volt battery. I put a piece of tape over the end so it's not ridiculously loud, but you can hear it, right?
Yeah,
Okay.
that's nice of you.
Yeah. So
Like
I'm gonna come over here, and yeah, I guess
Did the thing.
maybe. There's not a lot of places I can avoid echoes, so I'll just give it a shot. So I'm gonna swing it over my head, and I hopefully won't hit Paula or anything else, except for possibly the flag. Okay.
Yeah.
Yep. Better move over there. Okay. Move over here. So I'm gonna swing it over my head, and you listen for the buzzer. Again, echoes are a problem. What are you hearing?
The buzzer.
It's fainting slightly and then coming back. Like the intensity is like.
Is it the intensity? But what else is changing? Maybe if I speed it up.
The frequency.
Yeah, the pitch is changing.
Yeah.
As it moves towards you, the pitch goes what? Up or down?
Up.
Up. And it moves away from you, the pitch goes up or down? Down. Okay. So, yeah, this is a demonstration of the Doppler effect. Doppler effect. Yeah. So, if you ask, it's a demonstration of the Doppler effect. And the Doppler effect is what you get when your observer is moving towards a sound source, or a sound source is moving towards the observer, or you're moving away from a sound source, or the sound source is moving away from you. I have a question for you. What sound does a race car make?
Room.
Vroom. There's always two syllables. If you ask any 4-year-old what sound a race car makes, they always give you 2 syllables. Ver-oom.
Verdun.
Vroom.
Badoomba.
It's vroom. Why is it vroom?
Because that's here.
Yeah. It's ver coming towards you and driving away. Okay? It's ver coming towards you and driving away. We don't have to do this. Okay? But so that's the Doppler effect. You don't have to write all this stuff down, obviously. But when an object moves towards an observer, when a sound source moves towards an observer, or the observer moves towards the sound source, in other words, when the distance is getting smaller, you get an increase in pitch, an increase in frequency. If you want to prove it, then you can do this. You're like, here, take my pen. It's kind of fun.
You know, it's gonna be funny
Huh.
is when it's like October 15th this year, so it's gonna, the date's gonna be 10, 15, 20.
Cool.
Yeah, I just thought I'd show that.
What?
Thank you.
It's gonna count by 5s.
What is it?
Can I buy this one?
What?
Now, if an object moves, if a sound source moves away from an observer,
20.
or an observer moves away from the sound source, the waves are going to appear to be stretched, and you'll get a decrease in pitch, a decrease in frequency. So, you guys look like you wouldn't destroy each other's notes. I don't know.
Oh, I don't know about
You can
that.
try this later on. At lunchtime, you can try this. You get a piece of paper and you make a wave, and you're like, make a wave, and then your friend you can't see your friend, and your friend pulls the paper out while you're making the wave. What you're gonna find though is if you're making the wave and they pull the same direction as the wave's gonna get squished. And if you're making a wave and they pull the opposite direction of the wave's gonna get stretched out. And that's what's happening. So when I'm moving towards you, my frequency goes up. When I'm moving away from you, my frequency goes down. That's the Doppler effect. This is why all race cars make 2 noises. They make a ver coming towards you and an going away. The beeper should have sounded higher coming towards you and less high going away.
Does it also have to do with speed? Like,
Mhm.
if you're just like standing here and like, moving back and forth, that's not going to do that much of a pitch change, right?
Right. So because the speed of sound is so relatively slow, at 340 meters per second, when you have a fast-moving object like a race car moving at 40 or 50 meters per second, that's a pretty good chunk of the original speed of the wave. So you compress the wave quite a lot, or stretch the wave out quite a lot. This happens all out with aircraft too, and I'll talk about that in a little bit. Okay, questions?
Will you just give us time to write the bottom 2?
Yes, the bottom 2, you can write the bottom 2. Yeah, again, I realize you think sound moves pretty fast, and it does in a room like this, you know, thank goodness, otherwise people who are blind would not be able to use their tap, 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 tap. They would be like, tap, wait a little bit, tap. So they tap, tap, tap. And Daredevil would have a lot of trouble time doing Kung Fu if sound didn't move really fast. So it does move
Get his show canceled, like, in real life.
relatively fast. But in the grand scheme of things, it's pretty easy to exceed the speed of sound. You do it all the time. So when you get out of the shower at the YMCA and you roll up that towel and you snap each other's butts, you like doing that, right?
Yeah.
I know how you are. Or maybe when so some of you, like, you're on the swim team, you're like, roll up the towel and go, when you, that little end of the towel that goes out and then it gets snapped back really fast, that's breaking the speed of sound. I am absolutely serious. Breaking the speed of sound. And if you want to know how to make a whip, I used to make them. They're actually kind of fun. If you can make a rubber band whip, which is basically just a rubber band with a piece of string on it. Then you can go back and you go, phew, and it goes out and it stretches the rubber band and it brings it back and the end goes snap. That's breaking the sound barrier. Yeah.
Oh, okay. So I was about to say, I think it's going past the speech and making the sound very different. That's what I was going to say.
It depends on how big your wave is, and we'll talk about that. So there, if you don't understand what varoom, that's a varoom. So person A, the waves for person A are being compressed because the sound is like the car's going burp, 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 burp. And if you're moving towards the sound source, or the sound source is moving towards you, you're hearing burp, 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 burp. But if the sound source is moving away, you're hearing burp, 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 burp. So that's with the Doppler effect. Okay. So what about the sound effect, or what about the sound source of the person in the car? Does it change? No. Because the engine is the same distance away as you're driving. Scott.
So, just out of curiosity, whenever you see like a jet or something like that break the sound barrier, what is the weird little like particles or whatever you would call them? Like it's like
The cloud?
Yeah, the cloud.
I'm glad you asked. That?
Yeah.
We'll get to it.
Okay.
Yeah.
We'll get to it.
Yeah.
I mean, I'm seeing that sonic boom and I'm like,
All right. So if an object's not moving, so this is the plane just idling on the tarmac, keeping its engines warm while you're boarding the plane. Okay, no big deal. And then it starts to move, but it's not getting anywhere near the sound barrier. So it's cruising along, and if you were in front of the plane, you would hear a higher pitch rumble. If you were here behind the plane, you would hear a lower pitch rumble. Make sense? So the plane is constantly sending out these sound waves. Now, what is a sound wave?
Transfer
Yeah, all waves are a transfer of energy, but what is a sound wave? What is it?
it's vibrations across the medium.
Okay, so it's a vibrations in a medium. So let's think about what's going on with those mediums.
The molecules being moved by energy sources like that.
That's close enough, yeah. So the molecules are being moved by the wave energy. So, well, if we answer, we can. Yeah.
I did.
Look, I even reloaded it, so there's more Starburst and nerds in there. So the molecules are getting moved, and what you see, or if you could see at the molecular level, you would see at the compressions the molecules are close together, and then you would see after the compressions you see a what? Remember what that's called? A rarefaction. Now, not rarefaction, rarefaction, as in like that faction of air is rarefied. It's less of it. So after the compression, you see a rarefaction where the molecules are spread out. So what is a sound wave? A sound wave is a shock wave that compresses the molecules. Compresses in front, expands behind. So the compression causes the molecules to compress, and the rarefaction causes the molecules to expand. And when we say compression, what we're really talking about is high pressure. Compression, high pressure. Like what I'm trying to do with my wrist. Okay, put under compression. So high pressure when they're close together, low pressure when they're further apart. Does this make sense? Okay. So, what is that? Scott says, what is that cloud?
The
Sonic boom.
It's when a plane goes faster.
Yeah, so
Like
we're
the faster that he can go.
So we are breaking the sound barrier. We are breaking the sound barrier. We're exceeding the sound barrier. What is that cloud? Do you like chocolate? Tootsie Rolls? You're like, no, I like French chocolate. This is American chocolate. Yeah.
Isn't it like the sound where it gets caught onto the plane because like a draft or whatever?
Well, the plane's pushing the molecules apart. So as the plane travels, the wings, the cockpit, the fuel tanks, whatever, they are pushing the molecules together as they're traveling faster than the speed of sound. What I want to know is, this cloud you see, what is it?
Did it compress it so much to where like the pressure in that space of air was able to condense the water molecules into a cloud?
You're getting there.
Oh,
You're not quite there.
you're getting.
Okay, here we go. Oh no, I have to make weight. Oh
It
no.
is water.
Yeah, I can't even have this.
They're water molecules. They're absolutely water molecules. But they're not a compression. You ever watch the news article or news weather reports and they say it's low pressure? What kind of weather do you have when it's low pressure?
Overcast.
It's overcast. There's clouds. What kind of weather do you have when it's high pressure? It's sunny. So here's your compression
The molecules
and
apart.
here's your rarefaction. So as the plane breaks the sound barrier, you have a little compression right here and a little rarefaction back here. You have a big compression right here and a big rarefaction right behind it. That cloud, when something breaks the sound barrier, you are seeing the rarefactions behind the compressions. Does that make sense? Would you like to see it in? Would you like to see it in from YouTube?
What?
Yes.
So this is a aircraft.
Sonic boom.
Let's see if the video is going to work today. You never really know if the video is going to work. So this slides over here. There we go.
Makes sense, but I don't know.
All right.
Whoa.
Fake nation.
This is for
Okay,
racing.
so this is an F-14 breaking the sound barrier not a quarter mile from the deck of an aircraft carrier. Yeah, hopefully those guys were wearing their hearing protection, because that would be loud. But he breaks it, he slows down, and he breaks it again. So he breaks it, and then he slows down and breaks it again. And there are individuals who have done the math and like doing geometry, and they can look at that angle and they can say, based on this angle, I can tell you how fast he's going.
That's a lot of math.
It's probably in one of these textbooks around the room too. But yeah, based on this angle right there, you can tell how fast an aircraft is moving. So again, here's the compression, and what you're seeing back here is the rarefaction. As the air molecules are allowed to expand, they condense into water droplets.
So
Yeah.
if he was going faster, would the cloud be more like pinched?
Yep. Scott.
So he keeps breaking it and slowing down then breaking it. Was he just doing that for show, or is he required to do that? Like, what would happen if you just broke the sound barrier, didn't slow down, you just kept going?
Now I'm not in the
Going
Navy,
really fast.
but I would
Yeah.
bet, based on Top Gun, that breaking the sound barrier near a tower is a really bad idea, because you're sending out a shockwave that could easily break glass. So I think this pilot was doing it for show, just to like, this is what happens, everybody. Let's show the recruits who've never seen it before.
So nothing bad would happen if you broke the sound
Then you'd be
barrier?
like-
Oh, absolutely. Lots of bad things happen when you break the sound barrier
No, like to the aircraft.
to the aircraft.
Oh.
Well,
Earmuff.
Aircraft-
that's an excellent question. So that's the next thing we need to talk about. I'm going to talk about it right now.
Yes.
So why don't commercial aircraft break the sound barrier?
Because it's so
Because
high
they all
up.
break you.
If you looked at the wings of a commercial aircraft, they look kind of like that, right? Okay, and the back one might have another one that looks kind of like that. So these wings are not designed to break the sound barrier. However, there's a vehicle called the Concorde that is a commercial airliner, and its wings look like this.
It's like a paper air?
If you were to go bow hunting, and you wanted to make sure your arrow stuck as deep into the tree or as deep into the animal you were hunting as possible, would you want to use a wing, a tip that looks like this, or a tip that looks like this?
Like that.
Right.
On the left.
On this one, right? It looks like it could get through more.
That's more
Like,
piercing.
if you were making a house, would you want to select nails that look like this, or nails that look like that?
The one on the right.
Oh.
Yeah. So what does an aircraft have to do to break the sound barrier?
Has to,
Have barrels on it.
because we always refer to it as a barrier, right?
Mm-hmm.
You have to pierce through it, or?
Exactly. You have to punch through a whole bunch of very high pressure air. You have to punch through a whole bunch of very high pressure air. And that's not easy to do. And for the longest time, well, the longest time being about 5 or 6 years, back in the 50s, it was believed that we could simply not make a vehicle that would be able to break the sound barrier. Because all of that high pressure air would build up and build up and build up, and if you tried to punch through it, the wings would fly off. And that's what's going to happen if a commercial airliner tries to break the sound barrier. The wings are simply just going to get sheared right off. Imagine if a commercial airliner is designed to fly in the air would suddenly dump into water. Same thing's going to happen. Like, yeah, if you dump into water, so if you're going to jump into water, do you jump in like this?
No.
Or do you jump in like this? Yeah, you want to basically punch through. And so we have to make vehicles with swept wings and sharp points on the nose so they can punch through the high pressure air. Yeah.
Okay, so you said that, so if we were able to like have a commercial airline go the speed of light, and it's like, it looks like that, would it be like?
We're talking about light or sound?
Sound.
Okay, speed of sound, okay.
Okay, would that be bad because breaking the sound barrier, it happens at different points on the plane, and it could potentially like, I don't know, rupture it or something?
Okay, two things.
Yeah.
The reason that we don't fly the Concorde anymore,
Oh.
it was invented in the 70s, built in the 70s. It would basically go over the Atlantic in about 2.5 hours instead of like 8 hours.
Wow.
Yeah. Basically between Paris and London and New York, just living that triangle. And the reason that we don't do it anymore is this is a big one.
Of course, friction.
Yeah. So as you increase your velocity, your amount of aerodynamic drag basically increases with the square of velocity. So to go from 600 to 1200, you are quadrupling the amount of friction that's on the plane, so you are quadrupling the amount of fuel you need to get the plane up to that speed and keep it at that speed. Does that make sense?
Mm-hmm.
So that was the that was the biggest thing. Also, the engines. So a military aircraft, they have their engines rebuilt every 1,000 hours or so. Yeah, not miles. Every 1,000 hours or so, they have to have their engines rebuilt. Now, if you're talking about in a commercial sense, trying to make a profit, it's really hard to make a profit when your plane has to be rebuilt every few months. Because that's what would happen if the plane was constantly